Okay, now that we've dispensed with the properties of amines, we can talk about how we actually make them, which is, from my perspective, the fun part. So, first, a few that we've already talked about. One, we talked about using nitriles to make carboxylic acids and their derivatives in the previous chapter. So, here's an example of it. This is a straight up Sn2 reaction. The cyanide is a very good leaving group. We call it a cyanide before it comes in and nitrile after. This is covalent. This is not. So, the sodium is ionic. So, it's no longer a nucleophile here. It's a stable neutral compound, but it has pi bonds we can work with, so we can take them out. So this is one way of making them that we've talked about in the past, which is dealing with a nitrile. Next, along a similar vein, we basically take a carboxylic acid and turn it into an amide. Easiest way to do that is make the acid chloride here and then use ammonia to create the amide, and then use lithium aluminum hydride to reduce that down to the amine. This was unique in the carboxylic acid chapters because it's the only derivative that when you reduce it does not end up with an oxygen left on it here. It has the nitrogen because the nitrogen is less polar than the oxygen. So both methods here have lithium aluminum hydride, strong nucleophile, knocking out pi bonds at the end. This will not be the last time we see that trick, but that's the ones that we've talked about so far. So, next. Sn2 substitution. Okay. I warned you back in Organic 1 when we first covered that reaction that it's going to show up in every single chapter and it's that important. Well, surprise, surprise, here it is again. But there's a problem. And they're hinting at it at the bottom, but not showing it in the diagram here. And that is, this doesn't stop. It keeps going. Why? They're saying it down here, you can make a quaternary ammonium salt that way. Okay, fine. That implies it went 4 times from ammonia. Replaced 3 hydrogens and the lone pair with alkyl groups. Why? Why wouldn't you just stop with 1 if you could? And reality is, most of the time, you can't. So, what's going on there? Here's the problem. We end up with something that's more reactive. We had this problem with alkylation of aromatic rings with the Friedel-Crafts reaction. We ended up making a product that was more reactive than our starting material. When that happens, it's going to react again, and it's going to react faster than your starting material. So if I'm here with the original ammonia trying to compete with methylamine, it's going to lose. If I'm here with the original ammonia trying to compete with dimethylamine, it's going to lose. So this is faster still. Here, it's still going to happen, but it's slowing down a little bit because it's getting a little bit bulky. It's not slowing down because of electronic reasons. It's going to slow down because of steric reasons eventually. But methyl group is pretty small, so this probably would go all the way to 4. But getting 2 or 3 in is relatively easy because they're not going to be in each other's way until you have 3 of them in place, basically. So we really can't stop this with a single amine. We're really not even, most of the time, going to be able to stop it with 2 alkylations. There are exceptions and good ones, but it's not easy to do. Why? Why is an alkyl group activating this so much? And to answer that question, we have to go back in time a little bit. Remember this? Or this? Alkenes or cations are stabilized for the exact same reason. By alkyl groups. What is that reason? Hyperconjugation. Very good. This is the best of those 3. And go back to our amines. The more alkyl groups we have, the more hyperconjugation we have here. Why does that matter? Well, we're putting electron density into the nitrogen from each of those. So the nitrogen is going to be a little bit less, going to feel like it's a little bit more wealthy. It's going to be a little bit more generous. I mean, more likely to donate those electrons to the nucleophile than this, which is why ammonia will lose out eventually here. It has no hyperconjugation to help activate it. That's what's happening here. In the alkenes, in the cations, we're talking about hyperconjugation as a stabilizer. Here it's acting to activate the donation of that lone pair of electrons. Same principle, putting electron density in, but the nitrogen didn't really need the help. But it's going to use it. So, we got to keep that in mind. All right, so new ways to make stuff that we can get away with using the Sn2 reaction. The problem here is that we have extra hydrogens. So after each nucleophilic step, another one has to come in, act as a base, take the hydrogen off to give me back a neutral nitrogen. That's what we're seeing here. We go from neutral to cation to neutral to cation to neutral, and then eventually to a cation we can't neutralize because there's no more H to take off of it on the nitrogen at the end. So, all right, one way we can go about that is using an Sn2 reaction by having a nitrogen that has no H's. So what we're using here as a nucleophile is the azide ion. So it's this, the N3 minus ion, or if you want to draw it as a Lewis structure, it actually has a cationic nitrogen in the middle and anionic ones on both ends. So it has two possible nucleophilic sites. Basically, you know, one negative charge is going to be kind of canceling out the positive on the other, so we get a neutral compound in the end. So we're not really going to, this is really not capable of doing the reaction twice, even if it looks like it can. So we do that, we only get one nitrogen group, one carbon group attached to a nitrogen, and then we're going to reduce this off. We do that with either hydrogen and platinum. There's a couple of other different metals we could use here, or we use lithium aluminum hydride again. So if you're looking to remember things, lithium aluminum hydride keeps showing its face here. It's a really good way to knock pi bonds out. In this case, you can kind of see what's going to have to happen, because if I want that nitrogen by itself, the other stuff has to leave. Well, that's potentially nitrogen gas. It's probably not actually what's lost here, but that's one way to look at it. So because we're not introducing hydrogens until the nitrogen's already got a carbon on it in the next reaction, we don't have to worry about it going more than once. By the time we get this, we have no alkyl halide left, so it can't attach a second one. End of story. It only goes once. So here's what that looks like. Oh, sorry. This is the reduction that we're going through here. So here's the basics of that. We have the nucleophilic attack is an Sn2. Again, the nucleophile is symmetrical at that point. Then we're doing a lithium aluminum hydride trick and losing nitrogen gas. As I said, it's likely. It's likely to be what happens here. It's not really likely to be what happens with the H2, but we don't have to worry about that right this second. So we end up, after we've removed that, with another nitrogen anion, but there's nothing around to help it out except for water at the very end. So this is post-reaction. We don't put water in with lithium aluminum hydride unless we're interested in becoming, you know, student flambe. It's a good way to set a fire. This is pyrophoric, so very bad idea to have water around that at any point. So it's a reaction that at the end we have to be really, really careful with. Also, any reaction that gives off nitrogen gas is potentially going to blow the flask apart if you don't have a vent. So you got to be really careful setting this up that it's not a sealed system. Because if it is, this forms and it's going to want a whole lot of volume for that small amount of gas that's going to be forming. We really don't want to test out our glass to make sure it can handle that. So experimentally, we'd make sure we have some sort of vent on that. We probably would anyway if we're doing things right with air-sensitive materials and having a nitrogen source that's got a pressure regulator on it, but pressure relief on it. But just keep in mind, anytime you see a gaseous byproduct, that reaction must have some way to vent that. Otherwise, it potentially could blow apart. All right. Next method, similar concept, but different choice of reagents to do it with. The idea is we don't have any H's on the nitrogen after we remove this one, which is the only deprotonation in the whole reaction. We turn it into a nucleophile. So this is phthalimide. It comes from phthalic acid. It's relatively easy to make and relatively cheap to buy. Potassium hydroxide, very dirt cheap base. So making the actual nucleophile here is very simple. Probably can buy it as the nucleophile already deprotonated as a salt. I don't know. I've never had to work with this one. But the point is, very easy to make. And so then we've got another Sn2 reaction. Like I said before, it comes up in every chapter. Seemingly in every reaction, although obviously not really. But it comes up in a very large number of useful reactions, and this is another one. So same problem. We basically have put a nitrogen onto our group, and it has nowhere else where it can attach. It's not going to attach to an alkyl halide because this is resonating all the time. So it is not available. because we don't have to worry about it. So there's two ways to get that off there. One, we can do an acid hydrolysis, same as we did for regular amides. That will work, and then we have to then, we have to then make this basic to get that extra hydrogen off of it. Or two, we can actually treat this one with hydrazine, which takes out both carbonyls at one time and makes this particular six-membered ring. We're not really worried about that right now, but the point is it's a way of doing it without going through an acid step in case acid is a problem. And if we go through the acid version at the top, we have to get rid of it at the end. We're going to have to go here and treat this with base to get that extra hydrogen off there to give us back our neutral amine that we're trying to make in the first place. So our problem here is this. You may have already spotted it. We have this. We have this. I'm going to just make this the same one to just be consistent. I can do this with the azide. I can do this with the Gabriel. So either case here, and then, reduction here. Here, let's say we use the hydrazine method, whatever, it doesn't matter. And in all those cases, we're coming up to the exact same thing. We're coming up to a primary amine. And it's almost all I've got here. It's definitely all I've got here for the Gabriel. It's definitely all I'm getting here for the azide. It's really all I'm getting here for the amide. For the nitrile reduction. It's a little misleading here. I could have used a different amine, but the point is, for the most part, I have a lot of ways to get to a primary amine, and I basically have nothing that works well to get to a secondary or a tertiary amine. That's a problem, as you could probably guess. So, let's talk about how we fix it. Reductive amination. Now, in terms of making amines, this is definitely the most commonly useful version, because it gives you the ability to make something other than a primary amine. Now notice the example we're starting with, we're still making a primary amine. Don't worry, be patient. So we're doing something that we saw back in the aldehyde and ketone chapter, we're making an imine. So that's relatively simple. Go back and look at the mechanism on that. You know I'm going to ask it. Next, we're then taking that down by either using hydrogen or a stronger nucleophilic H- to reduce that pi bond, give us an H here, and end up with the extra H here. Wasn't there to begin with, so ends up here. Sorry. So the difference here, though, is that I can take this a different way. Now, in terms of reducing it, sodium borohydride is a bit problematic. Not problematic to do the reduction, but if I want to do this all in one flask, there's a problem. Sodium borohydride and acid don't get along. So if I'm going to use sodium borohydride here, I have to take this out and clean it up, and that is effort and time and chemicals. It's more expensive. We'd like to be able to do this all in one flask where we don't necessarily isolate this, we just take it forward. I can't do that with sodium borohydride. So the way that we deal with that, tweak it by switching out one of those H's for a cyano group. We end up with something that tolerates acids. A hydride reagent that's more acid tolerant, which means it can be put in here. It does not react with ketones, which means it will not touch this, but it will do this job very efficiently. It will take out the imine to the amine very efficiently, even in the presence of leftover acid. So it's a choice of reagents to deal with everything in one flask. That's what it means in situ. It means in the same reaction, without removing anything, cleaning it up. That the imine is formed temporarily. We're not actually separately pulling it out and looking at it. It's there. We form it. We break it all in the same reaction mixture. So the difference here, what makes this particularly useful? Yes, we can get to the primary amine. We had no shortage of ways of doing that, but these are the ones we couldn't really do any other way. That's really important because Secondary amines come up a lot in biochemical context, in pharmaceutical context. Less so tertiary ones, but still, being able to make them is critical. So we had to have a method to be able to make something other than just primary ones. This is a really good method. It's not particularly hard to do. The yields are typically very good, and it does not require harsh conditions, which means scaling it up is not going to cost you a fortune. It's always a question, if you have to scale up a reaction, well, I can heat things up to 200 degrees in the lab pretty easily. If I have to do that in a factory, it's going to cost the consumer more than they're going to be willing to pay because of the power bill. The heating bill would be too expensive. So we basically have to be really aware that extreme conditions in the lab are fine. Doing those in a factory is a safety issue and an expense issue depending on temperature. So this is a case where we don't have extreme temperatures. We don't have any real safety issues. So this is a case that this reaction could be done relatively easily on a ton scale. And it is done on a ton scale. So, as before, we have lots of ways to make primary amines. There's even others we didn't talk about in this chapter because your book didn't include them. But we have a lot of ways to put a group in that has a CH2 group here. So this is on top of the ones we already did, which was reducing an amide and reducing a nitrile. So we have 5 different ways to make this already. These are the 3 new ones. But if we want to actually make something that's secondary, well, we then become much more limited. We can make the primary by any method we want. Then, essentially, this is where we are for making a secondary and a tertiary. We just take it forward more than once if we need to. There are cases we would need a quaternary. That is much less common that we're going to need that. But if we did, we do a straight Sn2 alkylation with it. Depending on the R groups, we may have to heat it up because it's getting a little bit bulky and a little bit slow at that point. But so be it. Again, we don't need that one very often, but just keep it in mind, it's there. All right. So